Hello and welcome to DreamLab Knowledge. I'm so glad you're here with us tonight. Whether you're settling into bed after a long day, relaxing in your favorite chair, or simply seeking a moment of calm and wonder, you've come to the right place. Tonight, we're embarking on an extraordinary journey together, one that will take us deep into the heart of our planet, back through billions of years of time, and across landscapes that have risen, fallen, and transformed in ways that challenge our imagination. Close your eyes for a moment and feel the ground beneath your feet. Solid, unchanging, eternal, or so it seems. But beneath that reassuring stillness lies a planet in constant motion, a world where stone flows like honey, where mountains rise and fall like waves, where entire continents drift across the globe like leaves on a pond. Welcome to the realm of geology, where time stretches beyond human comprehension and the earth itself becomes a storyteller, whispering secrets that have been buried for billions of years. Tonight, we'll journey together through 100 remarkable facts about our planet's geology. Consider this your invitation to see the world differently, to understand that every rock beneath your hand, every mountain on the horizon, every grain of sand between your toes carries within it a story older than memory itself. So settle in, let your breathing slow, and prepare to discover the hidden world beneath our feet. Fact 1. The age of our ancient home. Our Earth is approximately 4.54 billion years old. 4.5 billion. Let that number settle in your mind for a moment. If you could count 1 year for every second, it would take you over 143 years to count to that number. This age wasn't determined by guesswork or ancient texts, but through the patient work of scientists examining the decay of radioactive isotopes in rocks and meteorites. The oldest rocks found on Earth's surface date back to about 4.28 billion years ago, discovered in the Jack Hills of Western Australia. These ancient zircon crystals survived when most of the early Earth's crust was still molten, still forming, still deciding what it wanted to be. Fact 2. Earth's layered architecture. Imagine cutting an apple in half and seeing its layers revealed. Earth is structured in a similar way, though far more complex. Our planet consists of 3 primary layers based on chemical composition: the crust, the mantle, and the core. The crust is Earth's thin outer shell, like the skin of that apple, ranging from just 3 miles thick beneath the oceans to about 44 miles thick under the continents. Beneath that lies the mantle, a thick layer of hot, dense rock that makes up an astounding 84% of Earth's volume and extends nearly 100 miles toward the planet's center. At the very heart lies the core, divided into a liquid outer core and a solid inner core, composed primarily of iron and nickel, where temperatures rival the surface of the Sun. Fact 3. The mantle's true color. Before studying geology, most people imagine Earth's mantle as a brownish or reddish mass, perhaps influenced by images of glowing lava. But the mantle actually has a greenish hue due to the prevalence of olivine, a mineral whose name comes from its olive green color. This mineral, composed of magnesium, iron, and silicate, dominates the upper mantle's composition. When you hold a piece of olivine in your hand, when you see that distinctive green crystal, you're looking at the same material that fills the vast majority of our planet's interior, the stone that flows and churns in slow, majestic currents beneath our feet. Fact 4. Mountains have roots. Here's something that might surprise you. Mountains work much like icebergs. Just as the vast majority of an iceberg exists beneath the water's surface, mountains have deep roots that extend far into Earth's mantle. Scientists discovered this when they measured gravity around mountain ranges and found it wasn't what they predicted. The gravitational measurements revealed that beneath towering peaks lie even more massive extensions of lighter crustal rock pushed deep into the denser mantle below. These roots can extend 5 to 6 times deeper than the mountain is tall, anchoring these geological giants in place. It's a phenomenon called isostasy, where the crust literally floats on the more fluid mantle beneath, and larger mountains need deeper roots to maintain their equilibrium. Fact 5. The inner core's curious growth. Deep within our planet, nearly 3,200 miles below the surface, the inner core is growing, but not uniformly. This solid sphere of iron and nickel, about 1,100 miles thick, increases by approximately 1 millimeter every year as bits of the liquid outer core solidify against it. But here's where it gets fascinating. This growth isn't even. The inner core grows in lumps and bunches, influenced by the churning mantle thousands of miles above. Growth concentrates more heavily around areas where tectonic plates are being subducted, pulled down into the mantle, while areas beneath superplumes of rising hot mantle rock see less solidification. The inner core itself is divided into hemispheres with different crystalline structures, and the Western Hemisphere appears to be crystallizing more quickly than the eastern side. Ketas. Fact 6. When iron melted, about 500 million years after Earth formed, a pivotal moment occurred in our planet's history, an event geologists call the Iron Catastrophe. As radioactive decay and the compression of space rocks heated the young Earth, temperatures eventually reached the melting point of iron, around 2,800 degrees Fahrenheit. When that happened, something remarkable occurred. The heavy iron, now liquid, began to sink toward the planet's center, while lighter, rocky materials rose toward the surface. This segregation of materials, this great sorting, created Earth's layered structure. It was a catastrophe in the sense that it was sudden and dramatic on geological timescales, but it was also the birth of Earth as we know it, the moment when our planet developed its core, its mantle, and ultimately its magnetic field. Fact 7. The magnetic shield. Earth's magnetic field, that invisible force that guides compass needles and protects us from solar radiation, is generated by the movement of the liquid outer core. As our planet rotates, the 1,100-mile thick layer of molten iron and nickel churns and flows, creating electric currents that generate a magnetic field extending thousands of miles into space. This field, called the magnetosphere, acts as an invisible shield, deflecting harmful solar wind and cosmic radiation that would otherwise strip away our atmosphere. Just as likely happened to Mars billions of years ago. The field was established approximately 3.5 billion years ago, and without it, life as we know it probably could never have evolved on Earth's surface. Earth. Fact 8. Wandering poles, Earth's magnetic poles, don't stay still. They wander, drifting across the planet's surface at varying speeds. Currently, the North Magnetic Pole is moving from Canada towards Siberia at a rate of about 35 miles per year, and this movement has accelerated in recent decades. But even more dramatically, every few 100,000 years on average, Earth's magnetic poles completely reverse. North becomes south, and south becomes north. We know this happened because certain minerals in cooling lava act like tiny compasses, aligning with Earth's magnetic field at the time they solidify. When geologists examine ancient lava flows, they find layers where the magnetic minerals point in opposite directions, evidence of these great reversals. The last reversal occurred about 0,000 years ago, and while we can't predict when the next one will happen, scientists have noted that Earth's magnetic field has weakened by about 9% over the past 2 centuries. Fact 9. The Mohorovičić discontinuity between Earth's crust and mantle lies a boundary with an intimidating name: the Mohorovičić discontinuity, usually mercifully shortened to the Moho. This boundary, named after Croatian scientist Andrija Mohorovičić, who discovered it in 1909, marks a distinct change in rock types and properties. At the Moho, seismic waves suddenly speed up, revealing that they've passed from the crust's rocks into the denser rocks of the mantle. No one has ever actually seen the Moho directly, though not for lack of trying. The deepest hole ever drilled, the Kola super deep borehole in Russia, reached about 7.5 miles down, but still didn't breach the crust. The Moho lies much deeper in most places, especially under continents where it can be 30 miles or more beneath the surface. Fact 10. Convection's grand dance. The mantle isn't static. Despite being solid rock, it flows, moving in vast convection currents over millions of years with the consistency of something like caramel or cold honey. Heat from Earth's core warms the bottom layers of the mantle, causing the rock to expand, become less dense, and slowly rise. As this material rises over millions of years, it cools, becomes denser, and eventually sinks back down. This grand circulation, this slow-motion dance of stone, is what drives plate tectonics on the surface. Hot material rises in mantle plumes, while cooler, heavier material sinks at subduction zones. It's the same principle that causes water to circulate in a pot on the stove, only operating over timescales that make human history seem like a fleeting moment. Fact 11. Supercontinent Pangaea, around 335 to 175 million years ago, all of Earth's landmasses were joined together in a single supercontinent that geologists call Pangaea, from Greek words meaning all lands. Imagine standing on this ancient supercontinent. You could walk from what is now South America to Africa to India to Antarctica without ever encountering an ocean. This vast landmass was C-shaped, surrounded by a single world ocean called Panthalassa. The interior of Pangaea experienced extreme climates with scorching deserts and dramatic temperature swings because the land was so far from the moderating influence of the ocean. Pangaea began breaking apart about 200 million years ago, fragmenting into the continents we recognize today, which continue to drift across the planet's surface. Fact 12. The supercontinent cycle. Pangaea wasn't Earth's first supercontinent, and it won't be the last. Our planet goes through a cycle, gathering its land masses together and then breaking them apart again, roughly every 400 to 500 million years. Before Pangaea, there was Pannosia, assembled about 600 million years ago. Before that came Rodinia, which formed roughly 1 billion years ago. And before Rodinia, there were others, their names and configurations still being debated by geologists. Currently, our continents are spreading apart, but the cycle will eventually reverse. In about 200 to 300 million years, scientists predict the continents will collide again to form a new supercontinent, sometimes called Pangaea Proxima or Amasia, though its exact configuration remains a topic of scientific speculation and wonder. Fact 13. Continental drift. The idea that continents move across Earth's surface seems obvious now, but it was revolutionary and controversial when German meteorologist Alfred Wegener proposed it in 1912. Wegener noticed that the coastlines of South America and Africa fit together like puzzle pieces. He found identical fossil species on continents now separated by thousands of miles of ocean. He discovered geological formations that matched across continents. Yet when Wegener suggested that continents had once been joined and had since drifted apart, the scientific community largely rejected his ideas. The problem was that Wegener couldn't explain what force could move entire continents. It wasn't until the 1960s, decades after Wegener's death, that the theory of plate tectonics provided the mechanism he'd been missing, vindicated his insights, and revolutionized our understanding of our dynamic planet. Fact 14. Tectonic plates, Earth's lithosphere, the rigid outer shell comprising the crust and the uppermost mantle, is broken into 7 or 8 major plates and numerous smaller ones. These plates aren't standing still. They're constantly moving, sliding across the more ductile asthenosphere beneath them, at rates ranging from less than 1 inch to about 4 inches per year. That might not sound like much, but over millions of years, these slow movements reshape the entire planet. The Pacific Plate, the largest, covers about 20% of Earth's surface. Where plates collide, mountains rise and earthquakes shake the ground. Where they pull apart, new crust forms and ocean basins widen. Where they slide past each other, faults open and the land trembles. This eternal motion, this restless choreography of stone, is what makes Earth a living, dynamic world. Fact 15. The ring of fire surrounding the Pacific Ocean, like a vast horseshoe, stretches the ring of fire, a 25,000-mile zone where tectonic plates meet, collide, and subduct. This region is home to about 75% of the world's active volcanoes and 90% of Earth's earthquakes. The Ring of Fire includes more than 450 volcanoes, from Alaska's Aleutian Islands down through the western coasts of North and South America, across to Japan, Indonesia, and New Zealand. The reason for all this activity is straightforward. The Pacific Plate is slowly being consumed, subducting beneath the plates surrounding it. As the Pacific Plate slides under other plates, it melts, creating magma that rises to form volcanic arcs and causing earthquakes as the plates grind against each other. Fact 16. The San Andreas Fault, cutting through California for about 800 miles. The San Andreas Fault marks the boundary where the Pacific Plate slides past the North American Plate. This is a transform boundary where plates move horizontally rather than colliding or separating. The Pacific Plate is moving northwestward relative to the North American Plate at about 2 inches per year. That might sound modest, but it means that in about 15 million years, Los Angeles and San Francisco will be neighbors, moved together by the inexorable grinding of tectonic plates. Despite what disaster movies suggest, the San Andreas Fault cannot produce tsunamis because it only moves laterally, not vertically. But it can and does produce major earthquakes, and geologists consider it almost certain that California will experience another significant quake on the San Andreas Fault in the coming decades. Fact 17. How mountains form. Mountains are born from the collision of tectonic plates, rising where the crust crumples and folds like paper pushed together. The Himalayas, Earth's highest mountain range, formed when the Indian Plate crashed into the Eurasian Plate beginning about 50 million years ago. This collision continues today, pushing the Himalayas higher at a rate of about 1 inch per year. The Andes Mountains form differently through subduction, where the oceanic Nazca Plate slides beneath the South American Plate, creating volcanic mountains along the plate boundary. The Appalachian Mountains in eastern North America were once as tall as the Himalayas, but have been worn down by hundreds of millions of years of erosion. Each mountain range tells a story of plate collisions, volcanic activity, and the patient work of wind and water sculpting stone. Fact 18. Earth's highest peak, Mount Everest, standing at 29,032 feet above sea level, is Earth's tallest mountain as measured from sea level. but it's not the tallest mountain in the solar system. That distinction belongs to Olympus Mons on Mars, a shield volcano that towers nearly 16 miles high, about 3 times taller than Everest. And if we measure mountains from their base rather than from sea level, Mauna Kea in Hawaii takes the crown. This massive shield volcano rises 33,500 feet from the ocean floor to its summit, with only about 13,800 feet above water. More than half of Mauna Kea is submerged, hidden beneath the Pacific Ocean, yet it stands as Earth's tallest mountain when measured from its true base. Fact 19. The 3 rock types. All rocks on Earth fall into 3 basic categories based on how they form. Igneous rocks crystallize from molten magma, either beneath the surface as intrusive rocks, like granite, or on the surface as extrusive rocks, like basalt. Sedimentary rocks form when particles of other rocks or the remains of living things accumulate in layers and are compressed and cemented together over time, creating rocks like sandstone, limestone, and shale. Metamorphic rocks are created when existing rocks are transformed by intense heat, pressure, or chemical processes deep within the crust, turning limestone into marble, sandstone into quartzite, and shale into slate. These 3 rock types are constantly being recycled through what geologists call the rock cycle, where igneous rocks erode to form sediments. Sediments compact into sedimentary rocks. Heat and pressure transform rocks into metamorphic varieties, and melting returns any rock type to magma. Fact 20. Volcanic origins. More than 80% of Earth's surface, both above and below sea level, is of volcanic origin. The rocks beneath your feet, whether you live in Oregon or Indonesia or Iceland, likely came from ancient volcanic activity. Volcanoes have been Earth's architects, building continents, creating islands, and releasing gases that formed our early atmosphere and oceans. Without volcanic activity, Earth would be a very different world. The water you drink, the air you breathe, the solid ground you walk upon, all owe their existence in part to billions of years of volcanic processes. Volcanoes continue to shape our world today, creating new land, enriching soils with minerals, and reminding us that beneath Earth's seemingly solid surface lies a restless, creative force. Fact 21. The vocabulary of lava geologists have borrowed words from Hawaiian to describe different types of lava. Pahoehoe, pronounced pahoihoi, is smooth, ropey lava that forms when the top surface cools and wrinkles while hot lava continues flowing beneath. Walk across a Pahoeho flow and you'll see swirls and coils frozen in stone, looking almost like twisted fabric. A'a, pronounced AHR, is rough, jagged lava that forms a clinkery, broken surface as it cools. Walking across an ACA flow will tear up your shoes, cut your hands, and generally make you appreciate the less hostile Pahoeho. The names are fitting. A supposedly comes from the sound you make when trying to walk across it barefoot. These Hawaiian terms have become standard geological terminology worldwide because Hawaii's volcanoes provide some of the most accessible and well-studied examples of these lava types. Fact 22. Diamonds from the deep diamonds form under extraordinary conditions in Earth's mantle, typically at depths between 90 and 120 miles below the surface, where pressure exceeds 725,000 pounds per square inch and temperatures soar above 2,000 degrees Fahrenheit. At these conditions, carbon atoms bond in a way that creates diamonds' characteristic hardness and crystal structure. But how do these deep forming gems reach the surface where we can find them? They're brought up by volcanic eruptions, specifically by a type of volcanic pipe called a kimberlite pipe. These eruptions are rare and violent, moving material from the mantle to the surface so quickly that the diamonds don't have time to convert back into graphite. Most diamonds found today formed between 1 and 3 billion years ago, ancient crystals that witnessed the Earth when it was young. Fact 23. Mineral diversity. Scientists have identified more than 4,000 different minerals on Earth, each with its own unique chemical composition and crystal structure. These minerals are the building blocks of rocks, combining in different proportions and arrangements to create the incredible variety of stone we see around us. Some minerals are common, like quartz, which forms much of the sand on beaches and makes up a significant portion of granite. Others are incredibly rare, found in only a few locations on Earth. New minerals are still being discovered, usually in extreme geological environments or in recently examined meteorites. Each mineral has properties that make it unique. Its hardness, its crystal form, its color, its luster, the way it breaks, the way it forms. Learning to identify minerals is like learning to read Earth's vocabulary, understanding the words with which our Magiti planet writes its story. Handada. Fact 24. Quartz, the common crystal. Despite the diversity of minerals, Quartz is by far the most abundant mineral in Earth's continental crust. This silicon dioxide crystal appears in many varieties, from clear rock crystal to purple amethyst to pink rose quartz to the multicolored layers of agate. Quartz is hard, 7 on the Mohs hardness scale, chemically resistant and stable at Earth's surface, which is why it accumulates as sand on beaches after other minerals have weathered away. When you walk on a sandy beach, you're likely walking on billions of tiny quartz crystals, each one a miniature 6-sided prism, each one tough enough to survive when softer minerals have crumbled to dust. Quartz's abundance and properties have made it useful to humans throughout history, from Stone Age tools to modern silicon computer chips. Fact 25. The Mohs scale. In 1812, German mineralogist Friedrich Mohs created a scale to measure mineral hardness based on which minerals could scratch others. His scale ranges from 1, talc, so soft you can mark it with a fingernail, to 10, diamond, the hardest natural substance. This simple scale is still used today. Gypsum rates a 2, a copper penny about 3, window glass 5.5, steel 7, and corundum, ruby and sapphire 9. Each mineral on the scale can scratch any mineral with a lower number but will be scratched by any mineral with a higher number. The scale is logarithmic, meaning that each step represents a much larger difference than a simple numerical progression. Diamond at 10 isn't just slightly harder than corundum at 9. It's actually many times harder. This scale helps geologists identify unknown minerals in the field and understand how different stones will behave when exposed to natural forces. Fact 26. Gemstone formation. Most gemstones form deep underground through various geological processes. Igneous gemstones, like diamonds and peridot, crystallize from molten material in the mantle. Metamorphic gemstones, like ruby, sapphire, and garnet, form when existing rocks are transformed by heat and pressure. Hydrothermal gemstones, like emerald and topaz, grow when mineral-rich hot water seeps into cracks and cavities in rocks, cooling and depositing crystals. Some gemstones, like opal, form through sedimentary processes as silica-rich water deposits layer after layer of microscopic spheres. What makes a mineral a gemstone? Beauty, rarity, and durability. A gem must be beautiful enough to desire, rare enough to be valuable, and durable enough to last. The Colombian emerald mines, famous for producing some of the world's finest emeralds extract these green beryls from hydrothermal deposits where chromium-rich fluids interacted with existing rocks millions of years ago. Fact 27. Coprolites. One of geology's more amusing terms is coprolite, which refers to fossilized feces. These ancient bathroom remains might sound unpleasant, but they're actually valuable to paleontologists because they provide direct evidence of what ancient animals ate. By examining coprolites under microscopes, scientists can identify plant remains, bone fragments, scales, and other dietary evidence preserved for millions of years. Large coprolites found in Cretaceous rocks likely came from dinosaurs. Smaller ones might be from ancient mammals or reptiles. Some coprolites are fossilized well enough to be polished and sold as novelty items. It's a reminder that geology studies everything that becomes preserved in rock, the magnificent and the mundane, the beautiful and the biological, all contributing to our understanding of Earth's past. Fact 28. Fossils as time capsules. Fossils are the preserved remains or traces of ancient life, and they're one of geology's most powerful tools for understanding Earth's history. The oldest fossils are stromatolites, layered structures created by bacteria dating back about 3.5 billion years. For most of Earth's history, life was simple, microscopic, and not particularly prone to fossilization. But about 40 million years ago, during what's called the Cambrian explosion, life became abundant and diverse enough to leave a rich fossil record. From that point forward, fossils allow geologists to date rocks, understand ancient environments, track evolutionary changes, and reconstruct vanished worlds. Each fossil is a messenger from the past, carrying information about what lived, where it lived, when it lived, and what the world was like at that moment, frozen in stone. Fact 29. Index fossils. Some fossils are particularly useful for dating rocks because the organisms that created them lived for a geologically brief period but spread widely across the planet. These are called index fossils. Trilobites, those fascinating arthropods that dominated Paleozoic seas, make excellent index fossils because different species appeared and went extinct at specific times. Ammonites, spiral-shelled cephalopods related to modern nautilus, serve the same purpose for Mesozoic rocks. When geologists find these fossils, they can immediately narrow down the age of the rocks containing them, sometimes to within a few million years. It's like finding a dated bookmark preserved within Earth's stone library, helping us place each page of geological history in its proper sequence. Fact 30. The geologic timescale. To organize Earth's vast history, geologists have developed the geologic timescale, dividing the planet's 0.34 billion years into hierarchical units. The largest divisions are eons. We currently live in the Phanerozoic eon, which began 541 million years ago, when complex life became abundant. Before that was the Proterozoic eon, and before that, the Archean eon. Eons are divided into eras: the Paleozoic, ancient life; Mesozoic, middle life; and Cenozoic, recent life. Eras are split into periods, periods into epochs, and epochs into ages. This system, refined over 2 centuries of geological work, allows scientists worldwide to communicate precisely about when events occurred in Earth's past. When a paleontologist mentions finding a fossil from the Devonian period, colleagues immediately understand she's talking about rocks formed between 419 and 359 million years ago. Mamauk Askamag. Fact 31. The Cambrian explosion. About 541 million years ago, something extraordinary happened in Earth's oceans. After more than 3 billion years of mostly simple, microscopic life, complex animals suddenly appeared in stunning diversity. This event, called the Cambrian explosion, saw the emergence of most major animal body plans we see today. Within a geologically brief period, perhaps 10 to 25 million years, oceans that had been dominated by bacteria, algae, and simple multicellular organisms suddenly teemed with trilobites, primitive fish, strange arthropods, and bizarre creatures that don't fit into any modern category. The Burgess Shale in Canada and the Xinjiang fauna in China preserve snapshots of this ancient explosion of life, offering us windows into the moment when Earth became a planet of animals, when complexity and diversity became defining features of life on our world. Fact 32. The Age of Dinosaurs. The Mesozoic era, spanning from about 252 to 66 million years ago, is often called the Age of Dinosaurs. This era saw these magnificent reptiles dominate terrestrial ecosystems in a way no single group has done before or since. The Mesozoic is divided into 3 periods: the Triassic, when dinosaurs first appeared; the Jurassic, when long-necked sauropods and plate-backed stegosaurs roamed; and the Cretaceous, which ended with the extinction of non-avian dinosaurs. During these 186 million years, dinosaurs evolved into an astounding variety of forms, from tiny feathered species, smaller than chickens, to the massive titanosaurs, the largest land animals ever to walk the earth. They occupied every terrestrial niche, from desert dwellers to forest browsers to apex predators. And then, 66 million years ago, they vanished, except for one lineage that survived: the birds, living dinosaurs that still fly among us today. Fact 33. The Great Dying. Earth's worst mass extinction occurred about 252 million years ago at the end of the Permian period. This event, sometimes called the Great Dying, wiped out roughly 96% of marine species and 70% of terrestrial vertebrate species. It took millions of years for Earth's ecosystems to recover. What caused this catastrophe? The evidence points to massive volcanic eruptions in what is now Siberia, releasing enormous amounts of carbon dioxide and sulfur dioxide, triggering climate change, ocean acidification, and oxygen depletion in the seas. The eruptions created the Siberian Traps, a vast province of flood basalts covering millions of square miles. This extinction cleared the way for the dinosaurs' rise in the Mesozoic, but at an almost unimaginable cost to the life that came before. Thus, Fact 34. The asteroid impact. 66 million years ago, an asteroid or comet at least 6 miles wide struck Earth near what is now the Yucatan Peninsula in Mexico. The impact created the Chicxulub crater, about 110 miles in diameter, and released energy equivalent to billions of atomic bombs. The impact sent debris into the atmosphere that blocked sunlight for months or years, causing temperatures to plummet and photosynthesis to cease. Massive tsunamis swept across coastlines. Wildfires raged across continents. Acid rain fell from skies choked with ash and sulfur. Within a relatively short time, perhaps just decades or centuries, 3/4 of Earth's species went extinct, including all non-avian dinosaurs. This catastrophe ended the Mesozoic era and opened the way for mammals, previously small and inconspicuous, to diversify and eventually give rise to humans. The boundary between the Cretaceous and Paleogene periods is marked worldwide by a thin layer of clay enriched with iridium, an element rare on Earth, but common in asteroids, physical evidence of the day the sky fell. Fact 35. Plate tectonics and life. The connection between plate tectonics and life goes deeper than simply shaping landscapes and climates. The movement of tectonic plates helps regulate Earth's temperature over geological timescales through a process called the carbonate-silicate cycle. When rain falls, it reacts with rocks, weathering them and carrying dissolved minerals to the ocean. There, marine organisms use these minerals to build shells and skeletons. When these organisms die, their remains accumulate on the seafloor. Eventually, seafloor spreading carries this carbon-rich sediment to subduction zones, where it's pulled down into the mantle. Some of this carbon is released back into the atmosphere through volcanic eruptions. This cycle acts as a planetary thermostat, removing carbon dioxide when Earth is warm and wet, speeding weathering, and adding it back through volcanism. Without plate tectonics maintaining this cycle, Earth might have frozen over completely or boiled into a hothouse, either scenario making life as we know it impossible. Fact 36. Earthquakes and seismic waves. When stress builds up along faults, the sudden release of that energy creates earthquakes. The point underground where the rupture begins is called the focus or hypocenter, and the point directly above it on Earth's surface is the epicenter. Earthquakes generate several types of seismic waves. Primary waves, or P waves, are compression waves that travel fastest and arrive first, moving through both solid rock and liquid. Secondary waves, or S waves, are shear waves that travel more slowly and can only move through solid material. Surface waves travel along Earth's surface and typically cause the most damage during earthquakes. By studying how these different waves travel through Earth, seismologists can determine the internal structure of our planet, mapping the boundaries between layers and identifying regions of different composition or temperature, essentially using earthquakes as a natural CT scan of Earth's interior. Shahada. Fact 37. Measuring earthquakes. The Richter scale, developed in 1935 by Charles Richter and Benno Gutenberg, was the first widely used system for measuring earthquake magnitude. It's a logarithmic scale, meaning each whole number increase represents a 10-fold increase in measured amplitude and about 32 times more energy release. An earthquake of magnitude 6 releases about 32 times more energy than a magnitude 5 quake. However, the Richter scale has limitations and tends to underestimate very large earthquakes. Today, seismologists prefer the moment magnitude scale, which better represents the actual energy released and doesn't saturate for large quakes. The moment magnitude scale considers the area of the fault that slipped, how far it moved, and the rigidity of the rocks involved. The largest earthquake ever recorded, the 1960 Valdivia earthquake in Chile, measured 2.5 on the moment magnitude scale. Fact 38. Global earthquake patterns. About 90% of the world's earthquakes occur along the Ring of Fire encircling the Pacific Ocean. Another significant zone of earthquake activity runs through the Mediterranean region and into Asia, following the collision zone between the African and Eurasian plates and continuing through the Himalayas. These patterns reflect the boundaries where tectonic plates meet, grind against each other, collide, or subduct. Earthquakes also occur at mid-ocean ridges, where plates pull apart, though these are generally smaller and less noticed because they happen underwater, far from populated areas. Even within plate interiors, earthquakes can occur, particularly in areas where ancient faults remain weakly active or where the removal of ice sheets after the last ice age continues to cause crustal rebound and adjustment. Fact 39. Tsunami generation tsunamis are often called tidal waves, but they have nothing to do with tides. These devastating waves are typically generated by underwater earthquakes that cause sudden vertical displacement of the seafloor. When a section of the seafloor suddenly shifts up or down during an earthquake at a subduction zone, it displaces the entire column of water above it. This displacement spreads outward as a series of waves. In deep ocean water, tsunami waves travel at speeds exceeding 500 miles per hour, but have such long wavelengths that ships barely notice their passage. As these waves approach shallow coastal waters, they slow down dramatically, but increase in height. The water can withdraw from the shore before the wave arrives, exposing the seafloor, a phenomenon that has lured curious observers to their deaths when the wave crashes inland moments later. The 2004 Indian Ocean tsunami killed more than 230,000 people across multiple countries, demonstrating the devastating power of these waves. Fact 40. Liquefaction. During earthquakes, some types of water-saturated sediments can temporarily lose their strength and behave like liquids, a phenomenon called liquefaction. Sandy or silty soils that are loosely packed and saturated with water are particularly susceptible. When seismic waves pass through these sediments, the shaking increases water pressure in the spaces between soil particles. If this pressure becomes high enough, it separates the particles, causing the soil to lose its strength and stiffness. buildings constructed on liquefied soil can sink, tilt, or collapse. Underground tanks and pipes can float upward. The ground can develop fissures and settlement. Liquefaction caused extensive damage during the 1964 Alaska earthquake, the 1989 Loma Prieta earthquake in California, and the 2011 Christchurch earthquake in New Zealand. Modern engineering practices now include soil testing and foundation design specifically to prevent liquefaction damage. Fact 41. Volcanic types. Not all volcanoes look or behave the same. Shield volcanoes, like those forming the Hawaiian Islands, have gentle slopes and erupt relatively fluid basaltic lava. These eruptions are generally less explosive, allowing lava to flow long distances and build broad, dome-shaped mountains. Stratovolcanoes, also called composite volcanoes, have steeper slopes and erupt more viscous lava along with ash, creating layered structures. Mount Fuji, Mount Rainier, and Mount Vesuvius are stratovolcanoes. These can produce violent explosive eruptions. Cinder cone volcanoes are small, steep-sided cones built from ejected lava fragments that solidify in the air and fall around the vent. Caldera-forming eruptions are the most catastrophic, occurring when huge amounts of magma erupt so rapidly that the ground collapses into the emptied magma chamber below, creating a large depression. Yellowstone's volcanic features sit within such a caldera, evidence of massive eruptions in the past. Fact 42. Volcanic explosivity. The Volcanic Explosivity Index, or VEI, ranks volcanic eruptions on a scale from 0 to 8 based on the volume of material ejected and the height of the eruption column. Each increase in VEI represents about a 10-fold increase in volume. A V0 eruption is non-explosive, like Hawaii's typical eruptions. A VEI 8 is termed mega-colossal, producing more than 240 cubic miles of ejecta. The 1815 eruption of Mount Tambora in Indonesia, a VEI 7 event, ejected so much material into the atmosphere that it caused the year without a summer in 1816, leading to crop failures and famines across the northern hemisphere. The 1883 Krakatoa eruption, also a VEI 7, generated tsunamis that killed tens of thousands and produced a sound heard 3,000 miles away. Yellowstone has produced VEI 8 eruptions in the past, though the probability of such an eruption occurring in any given millennium is extremely low. Fact 43. Pyroclastic flows during explosive volcanic eruptions. One of the most deadly phenomena is the pyroclastic flow, a fast-moving current of superheated gas, ash, and rock fragments racing down the volcano's slopes at speeds exceeding 100 miles per hour. These flows can reach temperatures of 1000 degrees Fahrenheit or more, instantly incinerating anything in their path. They're denser than air, so they hug the ground, flowing around obstacles and following valleys. Pyroclastic flows destroyed Pompeii and Herculaneum when Mount Vesuvius erupted in 79 AD, killing thousands of people who had no chance to escape. The flows moved so quickly that they preserved victims in the positions they held at the moment of death. More recently, pyroclastic flows from Mount Unsan in Japan and from Mount Pinatubo in the Philippines demonstrated that even with modern monitoring, these flows remain among the most dangerous volcanic hazards. The fact 44. Volcanic ash. Volcanic ash isn't actually ash in the conventional sense. It's made of tiny fragments of pulverized rock and glass created during explosive eruptions. Unlike the fluffy ash from a fireplace, volcanic ash is heavy, abrasive, and mildly corrosive. When wet, it becomes heavy and can cause roofs to collapse. It damages engines and machinery, clogs filters and air intakes, shorts out electrical equipment, and creates respiratory hazards. During the 2010 eruption of Geological in Iceland, volcanic ash in the atmosphere forced the closure of European airspace for 6 days, stranding millions of passengers and demonstrating that even relatively small eruptions in our interconnected world can have far-reaching consequences. Ash from large eruptions can circle the globe in the upper atmosphere, affecting weather patterns and creating spectacular sunsets as the particles scatter sunlight. Fact 45. Volcanic islands. Many islands are the peaks of underwater volcanoes rising from the ocean floor. The Hawaiian Islands, formed as the Pacific Plate moved over a hot spot, a relatively stationary plume of hot mantle material rising from deep within Earth. As the plate moved northwest, each volcano eventually drifted away from the hot spot, became extinct, and was replaced by a new volcano forming over the hot spot. This process created a chain of islands stretching across the Pacific, with the oldest islands to the northwest and the youngest, the Big Island of Hawaii, still growing over the hot spot today. A new underwater volcano, Loahi, is already forming southeast of the Big Island and will eventually emerge above the waves to become Hawaii's newest island, though not for tens of thousands of years. Fact 46. Geothermal energy volcanic regions contain tremendous thermal energy that can be harnessed for human use. In Iceland, a volcanic island straddling the mid-Atlantic ridge, geothermal energy provides about 25% of the nation's electricity and nearly 90% of its heating. Deep wells tap into hot water and steam heated by magma chambers beneath the surface. This clean, renewable energy has minimal environmental impact compared to fossil fuels. Other countries with significant geothermal resources include New Zealand, Kenya, the Philippines, and the United States. The geysers in California is the world's largest geothermal power plant complex. As technology improves, geothermal energy becomes viable in more locations, offering a sustainable way to convert Earth's internal heat into useful power. Fact 47. Hot springs and geysers. Where groundwater encounters hot rocks near the surface, it can emerge as hot springs. If the plumbing system is right and pressure builds up sufficiently, the water can erupt as a geyser, a dramatic fountain of hot water and steam. Yellowstone National Park contains more than half of the world's geysers, including Old Faithful, which erupts roughly every 90 minutes, shooting thousands of gallons of boiling water up to 180 feet into the air. Geysers require specific conditions: a heat source, an adequate water supply, a subsurface reservoir where water can collect, and a constricted pathway to the surface where pressure can build. These features are fragile and can be destroyed by earthquakes or human activity. The beautiful terraced pools at Yellowstone's Mammoth Hot Springs form as mineral-laden hot water emerges from the ground and deposits calcium carbonate, building intricate formations, layer by microscopic layer. Fact 48. Glaciers and ice ages. Though geology often focuses on stone, ice has been one of the most powerful sculptors of Earth's surface. Over the past 2.6 million years, during the Quaternary period, Earth has experienced cycles of glacial and interglacial periods. At the peak of the last glacial maximum, about 20,000 years ago, ice sheets covered large parts of North America, Europe, and Asia. These glaciers, some more than a mile thick, carved valleys, scraped surfaces smooth, transported massive boulders hundreds of miles, and created countless lakes and other landforms. The Great Lakes, those vast inland seas, are glacial features, carved and shaped by the weight and movement of ice. When the glaciers retreated, they left behind terminal moraines marking their furthest extent, drumlins and eskers revealing their direction of flow, and erratics, boulders carried far from their source and deposited in geologically alien environments. Ha! Fact 49. Glacial isostatic adjustment. The immense weight of ice sheets during glacial periods pressed down on Earth's crust, causing it to sink into the more fluid mantle beneath. When the ice melted and that weight was removed, the crust began slowly rebounding upward, a process called isostatic adjustment or glacial rebound. This process continues today in regions that were glaciated during the last ice age. Scandinavia is rising at rates up to half an inch per year. Hudson Bay in Canada is also rebounding. This rebound actually causes earthquakes in the Great Lakes region as the crust adjusts. In some coastal areas, ancient beaches now sit high above modern sea level, lifted by this ongoing rebound. The process operates on timescales of thousands to tens of thousands of years, another reminder that Earth's surface, seemingly so solid and stable, is actually in constant fluid motion. Fact 50. The Sahara's green past. The Sahara Desert, now one of Earth's harshest environments, was green and fertile as recently as 6,000 years ago. During the African humid period, increased monsoon rains transformed the Sahara into a landscape of lakes, rivers, and grasslands, supporting diverse wildlife and human populations. Cave paintings in the Sahara show giraffes, elephants, crocodiles, and cattle, animals that require substantial water and vegetation. Archaeological sites reveal fishing communities and agricultural settlements. This transformation occurred because of changes in Earth's orbital parameters, affecting the amount and distribution of solar radiation received in different seasons. As Earth's orbit gradually shifted, the monsoons weakened, the rains diminished, and the Sahara transformed into the desert we know today. This relatively recent change demonstrates how dramatically Earth's climate and landscapes can shift, even without human influence, simply through natural astronomical cycles interacting with Earth's atmosphere and oceans. Past us. Fact 51. Earth's oldest minerals. While the oldest rocks on Earth are about 4.28 billion years old, individual mineral grains can be even older. Zircon crystals, found in the Jack Hills of Western Australia, have been dated to 4.4 billion years old, just 160 million years after Earth formed. These tiny time capsules survived when the rest of the early Earth's crust was still molten or being constantly recycled. What makes zircons special is their remarkable durability and their incorporation of uranium, which decays into lead at a known rate, allowing scientists to date them with precision. Analysis of these ancient zircons suggests that liquid water, and possibly even a form of plate tectonics, existed on Earth far earlier than previously thought, pushing back the timeline for when our planet became hospitable to life. Fact 52. Weathering and erosion. While tectonic forces build mountains and create new landforms, weathering and erosion work constantly to tear them down. Weathering is the breakdown of rocks through physical, chemical, or biological processes. Physical weathering includes freeze-thaw cycles, where water seeps into cracks, freezes, expands, and splits the rock apart. Chemical weathering involves reactions between rock minerals and water, oxygen, or acids, transforming the minerals into new compounds. Biological weathering occurs when plant roots grow into cracks or when organisms produce acids that dissolve rock. Erosion is the transport of weathered material by wind, water, ice, or gravity. Together, these processes shape landscapes, creating valleys, canyons, beaches, and soil. Without weathering and erosion, mountains would stand forever, and the raw minerals essential for life would remain locked in stone. Fact 53. The Grand Canyon's story. The Grand Canyon, carved by the Colorado River over millions of years, exposes nearly 2 billion years of Earth's geological history. Stand on the rim and look down, and you're seeing layer upon layer of sedimentary rock, each representing a different environment, a different time. The deepest rocks, the Vishnu schist, are ancient metamorphic rocks, nearly 2 billion years old. Above them lie layers of sandstone, limestone, and shale, each telling stories of ancient seas, deserts, and river deltas. The canyon itself began forming about 5 to 6 million years ago, when the Colorado River established its current course and began cutting downward. The river didn't carve the canyon alone. Flash floods, rock falls, wind, and ice all contributed to widening and shaping this mile-deep chasm. The Grand Canyon reminds us that even the most massive landforms are temporary features, constantly being created and destroyed on geological timescales. Utuma. Fact 54. Karst landscapes. In regions with limestone or other soluble rocks, water creates distinctive landscapes called karst. Slightly acidic rainwater, which picks up carbon dioxide from the atmosphere and soil, slowly dissolves limestone. Over time, this chemical erosion creates sinkholes, disappearing streams, underground rivers, and vast cave systems. The Mammoth Cave System in Kentucky is the world's longest known cave system, with more than 400 miles of surveyed passages, all carved by water dissolving limestone over millions of years. Karst landscapes cover about 20% of Earth's land surface. While beautiful, karst regions present challenges for human development because the ground beneath can collapse suddenly when underground caverns become too large or when water tables drop. Spectacular karst towers rise from the landscape in southern China and Vietnam. Ancient limestone spires resisting dissolution while surrounding rock has been carried away. Fact 55. Stalactites and stalagmites. Inside limestone caves, water creates beautiful mineral formations called speleothems. Stalactites hang from cave ceilings, formed by water dripping from above. Each drop leaves behind a tiny amount of dissolved calcium carbonate. Over thousands of years, these deposits accumulate, building downward in icicle-like formations. Stalagmites grow upward from the cave floor, formed by the same process as water drips from above, and deposits minerals. Sometimes stalactites and stalagmites meet to form columns. Other speleothems include flowstones, draperies, and delicate formations like cave pearls and soda straws. These features grow incredibly slowly, typically less than an inch per century. The largest stalactite ever measured in the Jeta Grotto in Lebanon is over 27 feet long. Each of these formations is fragile, easily damaged by touching, and represents thousands to millions of years of patient, drop-by-drop deposition. Fact 56. Soil formation. Soil might seem humble, but it's one of Earth's most precious resources, and it has a geological origin. Soil forms from the weathering of bedrock, mixed with organic matter from decaying plants and animals. The process is remarkably slow. It can take hundreds to thousands of years to form just 1 inch of topsoil. Climate, parent rock type, topography, organisms, and time all influence soil characteristics. In tropical regions, intense weathering and heavy rainfall can produce deep but nutrient-poor soils. In volcanic regions, weathering of volcanic ash creates rich, fertile soils called andosols. These soils, found around the Ring of Fire, have excellent water retention and high nutrient levels, making them among the world's most productive agricultural lands. The recognition that soil is a geological resource that forms slowly but can be lost quickly through erosion has important implications for sustainable agriculture and land management. Fact 57. Desert formation deserts exist because of several different geological and atmospheric processes. Some deserts form in the rain shadows of mountain ranges, where moisture-laden air rises over mountains, cools, and drops its precipitation on the windward side, leaving the leeward side dry. Others form in subtropical high-pressure zones, where descending air warms and dries. Cold ocean currents can create coastal deserts by cooling air masses and reducing their ability to hold moisture. The Atacama Desert in Chile, one of Earth's driest places, receives less than half an inch of rain per year because of the cold Humboldt Current offshore and its location in a rain shadow. Some weather stations in the Atacama have never recorded rainfall. Despite the aridity, desert landscapes undergo weathering and erosion, often creating dramatic landforms like arches, hoodoos, and slot canyons, sculpted by occasional flash floods and wind-driven sand. Fact 58. Sand dunes come in various shapes determined by wind patterns, sand supply, and vegetation. Barchan dunes are crescent-shaped with horns pointing downwind, forming in areas with limited sand and consistent wind direction. Transverse dunes form perpendicular to wind direction where sand is abundant, creating long ridges. Star dunes develop where winds blow from multiple directions, creating star-shaped formations with arms radiating outward. Longitudinal dunes align parallel to prevailing winds and can extend for many miles. Sand dunes can reach impressive heights. The tallest dunes in the Badianjaran Desert of China rise more than 1,600 feet. Dunes migrate as wind carries sand grains up the gentle windward slope and deposits them on the steep slip face on the lee side. Ancient sand dunes, preserved in sandstone, provide evidence of past desert environments, wind patterns, and climate conditions. Fact 59. The Loess deposits. During ice ages, glaciers ground rocks into fine powder called glacial flour. Winds picked up this material and deposited it as loess wind-blown silt that can accumulate to great depths. The central United States, Central Europe, and especially northern China have thick loess deposits. In China's Loess Plateau, loess deposits exceed 650 feet in thickness, representing millions of years of dust accumulation. These deposits create fertile soil, but are highly susceptible to erosion, leading to dramatic landscape features and serious erosion problems. The material is so fine and uniform that it can stand in vertical cliffs, but heavy rainfall can trigger catastrophic erosion and mud flows. The Yellow River gets its name and color from the immense amount of loess-derived sediment it carries, about 1.6 billion tons per year, making it one of the most sediment-laden rivers on Earth. Fact 60. River systems and base-level rivers constantly work to erode their valleys down toward base level, typically sea level. As a river cuts downward, it creates a valley. If sea level drops, or if the land rises through tectonic uplift, the river responds by cutting deeper. If sea level rises or the land subsides, the river deposits sediment, building a floodplain. This constant adjustment creates various river features. Young rivers in mountainous areas flow rapidly through V-shaped valleys. Mature rivers meander across wide floodplains, creating oxbow lakes when curves are cut off. Old rivers near base level have minimal gradients and deposit fine sediment. Changes in base level can rejuvenate rivers, causing them to cut downward again. River terraces, former floodplains now elevated above the current river level, record these cycles of cutting and filling, preserving evidence of past river positions and climates. Fact 61. Deltas. Where rivers meet the ocean, they are often slow down and deposit their sediment load, building deltas. These features are named after the Greek letter delta because of the triangular shape of the Nile Delta. Deltas come in various forms depending on river discharge, wave energy, tidal range, and sediment load. The Mississippi River Delta has grown into the Gulf of Mexico for thousands of years, building land from sediment eroded from the North American interior. However, human activities, including levees that prevent natural flooding and sediment deposition, dams that trap sediment upstream, and fluid withdrawal that causes subsidence, have caused the delta to shrink in recent decades. Deltas are among Earth's most dynamic environments, constantly being built, reworked, and sometimes destroyed by storms. They're also incredibly productive ecosystems and agricultural areas. supporting dense human populations despite their vulnerability to flooding and sea level change. Fact 62. Barrier Islands. Along many coastlines, narrow strips of sand called barrier islands run parallel to the shore, separated from the mainland by lagoons or marshes. These islands form from sand deposited by waves and currents, often starting as submerged sandbars that grow upward until they breach the surface. Barrier islands migrate over time, moving landward through a process where storms wash sand over the island from the ocean side to the lagoon side. The Outer Banks of North Carolina are classic barrier islands, as are the Sea Islands of Georgia and South Carolina. These islands provide protection for the mainland from storms and waves, but they're also among Earth's most dynamic and hazardous places to build. Hurricanes can breach, fragment, or completely wash away barrier islands, as happens regularly along the Gulf and Atlantic coasts. Fact 63. Tsunamis and submarine landslides. While most tsunamis are generated by underwater earthquakes, submarine landslides can also create these devastating waves. The continental slopes, where the seafloor drops steeply from the continental shelf to the deep ocean, can accumulate unstable sediments. When these sediments fail, either triggered by earthquakes or simply through oversteepening, massive amounts of material can slide down the slope. The resulting tsunami can be even more destructive than those from earthquakes because the entire water column is displaced. The Storegga slide off Norway about 8,200 years ago involved about 7 to 70 cubic miles of sediment sliding down the continental slope. The resulting tsunami reached heights of up to 80 feet along some coastlines, inundating large areas of coastal Scandinavia and reached Scotland, 370 miles away. Evidence of this ancient tsunami is preserved in sand layers deposited far inland by the waves. Fact 64. Oceanic crust. The crust beneath the oceans is fundamentally different from continental crust. Oceanic crust is thin, typically just 3 to 6 miles thick, and composed primarily of basalt, a dark, dense volcanic rock. It's young in geological terms, with the oldest oceanic crust only about 200 million years old. Why so young? Because oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones. Continental crust, by contrast, can be billions of years old because it's less dense and doesn't subduct. The boundary between oceanic and continental crust is one of Earth's fundamental divisions. Continents are composed of granitic rocks, rich in silica and aluminum, while ocean floors are basaltic, rich in magnesium and iron. This difference in composition explains why continents stand high while ocean basins are deep. Fact 65. Mid-ocean ridges, the longest mountain range on Earth, isn't on land, but underwater. The mid-ocean ridge system stretches for about 40,000 miles, winding through all the ocean basins. At these divergent plate boundaries, tectonic plates pull apart and magma wells up from the mantle to create new oceanic crust. The process, called seafloor spreading, was discovered in the 1960s and provided crucial evidence for plate tectonics. As magma erupts and cools, it records Earth's magnetic field in the rocks. When geologists mapped magnetic patterns on the seafloor, they discovered symmetric stripes of normal and reversed magnetism on either side of the ridges, proving that new crust forms at the ridges and moves outward. This discovery revolutionized geology, transforming our understanding of Earth as a dynamic planet where the surface is constantly renewed. Fact 66. Hydrothermal vents. Along mid-ocean ridges, cold seawater seeps into cracks in the newly formed oceanic crust, gets heated by magma beneath, becomes chemically altered, and spews back out as hydrothermal vents. These vents, discovered in 1977, support remarkable ecosystems based on chemosynthesis rather than photosynthesis. Bacteria use the chemicals in the vent fluids, particularly hydrogen sulfide, as an energy source. These bacteria form the base of a food web that includes tube worms, clams, crabs, and fish, all thriving in complete darkness under crushing pressure. Some vents, called black smokers, emit superheated water reaching temperatures above 750 degrees Fahrenheit, laden with dissolved minerals that precipitate when the hot water meets cold seawater, creating chimney-like structures. These vents may have provided the energy and chemicals necessary for the origin of life on Earth, and similar environments might exist on ocean worlds elsewhere in our solar system. Fact 67. Deep sea trenches. The deepest parts of the ocean are trenches, formed where oceanic plates subduct beneath other plates. The Mariana Trench in the western Pacific is the deepest, with its lowest point, the Challenger Deep, reaching nearly 7 miles below sea level. The pressure at these depths exceeds 15,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. Despite these extreme conditions, life exists even in the trenches. Specialized organisms, including amphipods, fish, and microbial communities, have adapted to the darkness, cold, and crushing pressure. These trenches are sites of recycling, where oceanic crust and sediments are returned to the mantle, completing the plate tectonic cycle. They're also sites of powerful earthquakes, as the descending slab grinds against the overlying plate. Fact 68. Seamounts and guyos. Scattered across the ocean floor are thousands of seamounts, underwater mountains rising at least 300 feet above the surrounding seafloor. Many are extinct volcanoes. Some seamounts have flat tops and are called guyots, named after Swiss geologist Arnold Guyot. These flat tops were once at sea level, where wave action eroded the volcano's peak. As the oceanic plate moved and cooled, it sank, carrying the flattened volcano down into deeper water. The Pacific Ocean alone has an estimated 30,000 seamounts. These features affect ocean currents, create upwelling that brings nutrients to surface waters, and provide habitat for diverse marine life. Some seamounts are composed of rock types rich in valuable minerals, leading to interest in deep-sea mining, though the environmental impacts of such mining remain a major concern. Fact 69. Coral reefs and atolls. Coral reefs are geological structures built by living organisms. Coral polyps, tiny animals related to jellyfish, extract calcium carbonate from seawater to build protective skeletons. Over time, these skeletons accumulate, creating massive reef structures. Atolls are ring-shaped coral reefs that often enclose lagoons. Charles Darwin proposed that atolls form around volcanic islands. As the island sinks and erodes, the coral continues growing upward, eventually creating a ring of reef with no central island. This process was confirmed by drilling into atolls and finding volcanic rock beneath the coral. The Great Barrier Reef, the world's largest reef system, extends for about 1,400 miles along Australia's coast. It's composed of about 3,000 individual reefs and 900 islands, all built by countless generations of coral over thousands of years. Coral reefs support tremendous biodiversity and provide crucial ecosystem services, but they're threatened by climate change, ocean acidification, and pollution. Fact 70. Sea level changes. Sea level hasn't been constant through Earth's history. During ice ages, when vast amounts of water were locked in ice sheets, sea level dropped by 400 feet or more. Shorelines moved far out onto what is now continental shelf. Ancient river valleys carved across exposed shelves are now submerged. When ice sheets melted, sea levels rose dramatically. About 20,000 years ago, at the last glacial maximum, sea level was about 100 feet lower than today. As the ice melted, sea level rose rapidly, flooding coastal areas and creating new coastlines. This flooding separated Britain from continental Europe, created the modern outlines of continents, and forced human populations to migrate inland. Today, with ongoing climate warming, sea level is rising again at an accelerating rate, threatening coastal communities worldwide. The geological record shows that sea level can change dramatically over both short and long time scales, responding to ice volume, ocean temperatures, and tectonic processes. Fact 71. Isostasy, Earth's crust, floats on the denser mantle beneath in a state of equilibrium called isostasy. Think of blocks of wood floating in water. Thick blocks float higher than thin blocks, but they also extend deeper below the water's surface. Similarly, thick crustal blocks, like mountain ranges, float higher but also have deep roots extending into the mantle. When weight is added, such as ice sheets during glacial periods, the crust sinks. When weight is removed, the crust rebounds. This principle explains many geological observations, including why mountains have roots, why regions compressed by ice sheets are still rebounding thousands of years after the ice melted, and why volcanic islands slowly sink as they move away from hot spots and the underlying plate cools and contracts. Fact 72. Economic geology. Much of modern civilization depends on materials extracted from Earth's crust. Metals like iron, copper, aluminum, gold, silver, and rare earth elements are all geological products concentrated by various processes into ore deposits. Some deposits form from magmatic processes, where minerals crystallize from cooling magma. Others form from hydrothermal fluids that deposit minerals in cracks and cavities. Some are sedimentary, formed by weathering and concentration processes. Oil and natural gas are geological resources formed from the remains of ancient organisms buried and transformed under heat and pressure. Coal is compressed plant material from ancient swamps. Even the building materials we use, from limestone for cement to sand for glass and concrete, are geological products. Understanding how these resources form allows geologists to find new deposits and to extract them more efficiently. Fact 73. Oil and gas formation. Petroleum forms from the remains of tiny marine organisms that died and settled to the sea floor millions of years ago. As sediments buried these organic remains deeper, heat and pressure transformed them into hydrocarbons. This process requires specific conditions: enough organic matter, burial to the right depth where temperatures reach the oil window between about 140 to 300 degrees Fahrenheit, and time, typically millions of years. The hydrocarbons migrate upward through porous rock until they encounter an impermeable layer that traps them, creating oil and gas reservoirs. Not all organic-rich sediments become oil. If buried too shallow, they don't reach the temperatures needed. If buried too deep, the oil breaks down into natural gas or even just carbon. Most of the world's oil formed during specific periods when conditions were ideal, particularly during the Jurassic and Cretaceous periods when warm, shallow seas supported abundant marine life. Fact 74. Coal swamps coal is fossilized plant material, but not just any plant material. Most coal formed during the Carboniferous period, roughly 359 to 299 million years ago, when vast swamps covered much of the land. In these swamps, dead plant material accumulated faster than it could decay, creating thick layers of peat. Over millions of years, as more sediments buried these peat layers, heat and pressure gradually transformed them into coal. Different degrees of transformation created different types of coal. Lignite or brown coal is the youngest and softest. Bituminous coal is older and harder. Anthracite, the oldest and hardest, is almost pure carbon. The Carboniferous period was a unique time in Earth's history. Plants had evolved wood and bark, but fungi and bacteria hadn't yet evolved efficient ways to decompose these materials. This imbalance allowed massive amounts of plant carbon to be buried, eventually forming today's coal deposits. Fact 75. The carbon cycle. Carbon constantly cycles through Earth's systems, moving between the atmosphere, oceans, life, and rocks over vastly different timescales. The biological carbon cycle operates over years to decades as plants absorb CO2, animals eat plants and exhale CO2, and decomposition returns carbon to the atmosphere. The geological carbon cycle operates over millions of years. Carbon dioxide from the atmosphere dissolves in rainwater, weathers rocks, and gets carried to the ocean. Marine organisms use this carbon to build shells. When they die, their shells accumulate on the seafloor. Eventually, seafloor spreading carries this carbon to subduction zones, where some is recycled into the mantle and some returns to the atmosphere through volcanic eruptions. This long-term cycle helps regulate Earth's climate over geological timescales. Currently, humans are rapidly transferring carbon from the slow geological cycle, fossil fuels, to the fast atmospheric cycle, disrupting the balance that has maintained Earth's climate for millennia. That's it. Fact 76. Permafrost. In Earth's polar and high-altitude regions, ground that remains frozen for at least 2 consecutive years is called permafrost. This frozen soil can extend hundreds of feet deep and covers about 15% of the northern hemisphere's land area. Permafrost acts as a geological freezer, preserving organic matter that would otherwise decompose. Remarkably intact remains of Ice Age animals, including woolly mammoths with preserved soft tissue, have been found in Siberian permafrost. But permafrost is also a climate concern. As temperatures rise, permafrost thaws, allowing the organic matter it contains to decompose and release carbon dioxide and methane into the atmosphere. The thawing also creates engineering challenges, causing buildings, roads, and pipelines to sink and collapse. Some estimates suggest permafrost contains twice as much carbon as currently exists in Earth's atmosphere, making its fate crucial for future climate. Fact 77. Meteorite impacts throughout Earth's history. Our planet has been bombarded by asteroids and comets. While most objects burn up in the atmosphere, large ones reach the surface and create impact craters. Earth has about 90 confirmed impact craters, though erosion and plate tectonics have erased most ancient ones. The Chicxulub crater, created by the asteroid that contributed to the dinosaurs' extinction, is about 110 miles in diameter. The Vredefort crater in South Africa, formed about 2 billion years ago, is even larger at roughly 190 miles across, though erosion has heavily modified it. Impacts can have profound effects on Earth's geology and life. They create new rock types like impactites and suavites. They generate shock waves, tsunamis, and wildfires. They eject material into the atmosphere, potentially triggering climate changes. Small impacts occur frequently, large ones rarely, but given enough time, catastrophic impacts are inevitable. Fact 78. Tectites. When large meteorites strike Earth, they vaporize rock and eject it high into the atmosphere. Some of this material cools and solidifies during flight, falling back to Earth as tectites, glassy objects with distinctive shapes and compositions. Tectites are found in strewn fields, areas covering thousands of square miles associated with specific impact events. Australasian tectites, scattered across Southeast Asia and Australia, came from an impact about 800,000 years ago. North American tectites are about 35 million years old. Tectites differ from volcanic glass because they were melted by impact shock rather than by volcanic heat, and they often contain terrestrial material mixed with traces of the meteorite. Finding tectites helps geologists locate ancient impact craters that erosion has obscured or destroyed. Killed. Fact 79. Shocked quartz. Certain geological features can only form under the extreme pressures of meteorite impacts. Shocked quartz is one such indicator. When quartz grains experience the intense shock waves from an impact, they develop distinctive features called planar deformation features, parallel sets of microscopic fractures that don't occur in other geological settings. Finding shocked quartz in sedimentary layers provides strong evidence for impact events. Shocked quartz from the Chicxulub impact has been found in boundary layers around the world, helping confirm the impact hypothesis for the dinosaur extinction. Other minerals also show shock features, including diamond polymorphs that form only under extreme pressures. These impact signatures allow geologists to identify ancient impacts, even when the craters themselves have been destroyed. Fact 80. Mass extinctions. The fossil record reveals 5 major mass extinctions when Earth lost more than 75% of species within geologically short periods. The end Ordovician extinction, about 444 million years ago, was likely caused by glaciation and sea level changes. The late Devonian extinction occurred around 375 million years ago, possibly linked to asteroid impacts and oxygen depletion. The end Permian extinction, or Great Dying, wiped out 96% of marine species about 252 million years ago, caused by massive volcanic eruptions. The end Triassic extinction, about 201 million years ago, opened the way for dinosaurs to dominate. The end Cretaceous extinction, 6 million years ago, caused by the Chicxulub, Impact combined with volcanic eruptions in India ended the age of dinosaurs. These catastrophes reset evolution, eliminating dominant groups and allowing survivors to diversify. Some scientists argue we're now in a sixth mass extinction, this one caused by human activities. Fact 81. Radiometric dating. Before the development of radiometric dating, geologists could only determine the relative ages of rocks. They knew which rocks were older or younger based on their positions and fossils, but not their absolute ages. The discovery of radioactive decay changed everything. Some isotopes are unstable and decay at predictable rates into different elements. For example, uranium 238 decays to lead 206 with a half-life of 4.5 billion years. By measuring the ratio of parent to daughter isotopes in rocks or minerals, scientists can calculate when the minerals crystallized. Different isotopes with different half-lives are useful for different age ranges. Carbon-14, with its 5,030-year half-life, dates organic materials up to about 50,000 years old. Uranium-lead dating can measure ages of billions of years. This technology has revealed Earth's true age, the timing of evolutionary events, and the rates of geological processes. Fact 82. Stratigraphy. Stratigraphy, the study of rock layers, is fundamental to geology. The principle of superposition states that in undisturbed sequences, older rocks lie beneath younger rocks. The principle of original horizontality states that sediments are deposited in horizontal layers. The principle of lateral continuity suggests that sedimentary layers extend laterally until they thin out or encounter a barrier. The principle of cross-cutting relationships tells us that features cutting through rocks must be younger than those rocks. Using these principles, geologists can determine the sequence of events that created a landscape. Unconformities, where rock layers are missing due to erosion or non-deposition, reveal gaps in the geological record. Reading rock layers is like reading a book, though one with many pages torn out, water damaged, and out of order. The geologist's job is to reconstruct the story. Fact 83. Fossils and evolution. Fossils don't just tell us what organisms looked like. They reveal evolution in action. Transitional fossils show intermediate stages between different groups. Archaeopteryx from Jurassic rocks shows features of both dinosaurs and birds, with teeth, clawed wings, and a long bony tail from its dinosaur ancestry, and feathers and wishbone indicating its relationship to birds. Tectonic from Devonian rocks shows the transition from fish to tetrapods with fins that could support weight and a neck that allowed independent head movement. The fossil record shows that species change over time, that all life shares common ancestors, and that evolution proceeds through descent with modification. The sequence of fossils through time matches evolutionary predictions, with simple organisms appearing first, complex organisms later, and transitional forms appearing when and where predicted by evolutionary theory. Fact 84. Human evolution. The fossil record also documents human evolution. Our hominin ancestors diverged from other apes about 6 to 7 million years ago in Africa. The oldest well-documented hominin, Sahelanthropus chadensis, dates to about 7 million years ago. Australopithecus afarensis, including the famous Lucy skeleton, lived about 2.2 million years ago and walked upright but had a small brain. Various Homo species appeared starting about 2.8 million years ago. Homo erectus spread from Africa to Asia and Europe. Homo neanderthalensis, the Neanderthals, lived in Europe and Western Asia until about 40,000 years ago and interbred with modern humans, leaving traces of Neanderthal DNA in non-African populations today. Homo sapiens, our species, evolved in Africa about 300,000 years ago and spread across the globe, replacing or absorbing other hominin populations. Each fossil find adds details to this story, showing that human evolution was complex, involving multiple species and migrations. Fact 85. Amber preservation. Amber is fossilized tree resin, and it provides exceptional preservation of ancient life. Organisms trapped in sticky resin became entombed as the resin hardened over millions of years. Amber can preserve incredible detail, including soft tissues, colors, and DNA traces. Insects preserved in amber look almost alive, with compound eyes, delicate wings, and fine body hairs intact. Amber has preserved flowers, pollen, leaves, feathers, and even small vertebrates like lizards and frogs. Dominican amber, formed from legume tree resin about 15 to 20 million years ago, commonly contains perfectly preserved insects. Baltic amber, older at 35 to 40 million years, comes from coniferous forests. The oldest amber dates to about 220 million years ago. Amber fossils provide unique insights into ancient ecosystems, showing organisms and interactions rarely preserved in other types of fossils. Fact 86. The Burgess Shale. Some fossil sites provide extraordinary windows into ancient life. The Burgess Shale in British Columbia preserves soft-bodied organisms from the Cambrian period, about 108 million years ago. Normally, only hard parts like shells and bones fossilize, but unusual conditions in the Burgess Shale, including rapid burial in fine sediment in low oxygen conditions, preserved soft tissues. The fossils show bizarre creatures, unlike anything alive today, revealing the experimental nature of early animal evolution. Opabinia had 5 eyes and a grasping appendage extending from its head. Anomalocaris was the era's top predator, reaching over 3 feet long. Hallutigenia had spines on its back and legs underneath, though scientists initially reconstructed it upside down. These fossils revolutionized understanding of Cambrian life, showing that the explosion of diversity was even more dramatic and strange than previously imagined. And fact 87. Living fossils. Some organisms have changed little over vast spans of time, often called living fossils, though that term is somewhat misleading since all living species continue evolving. The horseshoe crab has maintained a similar body plan for about 450 million years. The coelacanth, a fish thought extinct for 66 million years until discovered alive in 1938, has changed little for hundreds of millions of years. Ginkgo trees have existed relatively unchanged for about 270 million years, surviving only in cultivation after going extinct in the wild. These organisms aren't evolutionary failures, they're success stories, finding ecological niches where their body plans continue working well. However, they have evolved at genetic and physiological levels, adapting to changing environments while maintaining recognizable forms. They remind us that evolution doesn't always mean dramatic change. Sometimes, the most successful strategy is refinement rather than transformation. Fact 88. Plate reconstructions. By combining evidence from paleomagnetics, matching geological formations across continents, fossil distributions, and seafloor spreading patterns, geologists can reconstruct how continents were positioned in the past. These reconstructions show that continents have been in constant motion throughout Earth's history. During the Proterozoic Aeon, continents assembled into supercontinents like Rodinia and then fragmented. During the Paleozoic era, fragments reassembled into Pangaea. Since then, Pangaea has broken apart into today's configuration. These reconstructions help explain many puzzling observations, like why identical fossil species appear on now separated continents, why similar rock formations and mountain belts line up across oceans, and why certain mineral deposits occur where they do. Looking forward, geologists can project plate movements into the future, predicting how continents will continue drifting and where they might eventually collide to form the next supercontinent. Fact 89. Wilson Cycle. The Wilson Cycle, named after geologist John Tuzo Wilson, describes the life cycle of ocean basins. It begins when continental rifting starts, creating a rift valley like the East African Rift. If rifting continues, the continent breaks apart and a narrow ocean forms like the Red Sea. As spreading continues, a mature ocean basin develops like the Atlantic. Eventually, subduction begins at the ocean margins and the ocean starts closing. As the ocean shrinks, the continents on either side approach each other. Finally, the continents collide, closing the ocean and creating a mountain range, like the Himalayas formed when India collided with Asia. The cycle can begin again when forces cause the newly formed supercontinent to rift apart. This cycle has operated throughout Earth's history, repeatedly assembling and dispersing continents, opening and closing ocean basins, with complete cycles taking hundreds of millions of years. Fact 90. Transform boundaries. At transform boundaries, tectonic plates slide horizontally past each other without creating or destroying crust. The San Andreas Fault is the most famous transform boundary, but many others exist, particularly offsetting segments of mid-ocean ridges. Transform faults are sites of frequent earthquakes as the plates grind past each other. Because the plates are moving laterally rather than converging or diverging, transform boundaries don't produce volcanism or create mountain ranges in the same way other boundaries do. However, the rock along transform faults becomes intensely fractured and altered by the grinding motion, creating fault zones that can be miles wide. In California, the San Andreas Fault Zone includes numerous parallel and subsidiary faults, creating a complex system where strain is distributed across multiple structures rather than concentrated on a single fault line. Fact 91. Ophiolites. Ophiolites are sections of oceanic crust and upper mantle that have been uplifted and exposed on land, usually during continent-continent collisions. These rare formations allow geologists to examine directly the layers of oceanic crust that normally lie hidden beneath miles of ocean water. An ophiolite sequence typically includes, from bottom to top, peridotite from the mantle, layered gabbros that crystallized in magma chambers, sheeted dikes that fed lava to the surface, pillow basalts erupted on the seafloor, and deep sea sediments. Famous ophiolites include those in Oman, Cyprus, and Newfoundland. Studying ophiolites has been crucial for understanding seafloor spreading and the composition of oceanic crust. They also often contain valuable mineral deposits, including copper and chromium ores, formed by hydrothermal processes at mid-ocean ridges. At sea. Fact 92. Mantle plumes. While most volcanic activity occurs at plate boundaries, some volcanoes occur in the middle of plates, far from any boundary. These volcanoes are thought to be fed by mantle plumes, columns of abnormally hot rock rising from deep in the mantle, possibly from the core mantle boundary, nearly 1,800 miles below the surface. As a plate moves over a stationary plume, a chain of volcanoes forms, with the youngest directly over the plume and older volcanoes trailing behind as the plate carries them away. The Hawaiian Islands formed this way, as did the Emperor Seamount Chain, extending northwest from Hawaii. Yellowstone is another hotspot, and the Snake River Plain records the track of the North American plate moving over it. Not all geologists agree that mantle plumes exist, and the debate continues, but they provide a compelling explanation for volcanic activity far from plate boundaries. Fact 93. Large igneous provinces. Several times in Earth's history, enormous volumes of magma have erupted, creating large igneous provinces. The Siberian Traps erupted about 252 million years ago, covered millions of square miles with lava up to 2 miles thick. These eruptions coincided with the end Permian mass extinction, suggesting the volcanic gases and climate changes they caused contributed to the catastrophe. The Deccan Traps in India erupted around the same time as the Chicxulub impact, about 66 million years ago, and may have combined with the impact to cause the end Cretaceous extinction. The Columbia River Basalt Group in the northwestern United States erupted about 15 to 17 million years ago, covering parts of Washington, Oregon, and Idaho with flood basalts. These massive eruptions represent catastrophic events, possibly caused by mantle plumes reaching the surface or by continental breakup, opening channels for deep magma to erupt. Fact 94. Earth's water origins. Where did Earth's water come from? This question has puzzled scientists for decades. One hypothesis suggests water was part of Earth from the beginning, incorporated into the minerals of the planetesimals that accreted to form our planet. Another proposes that water arrived later, delivered by comets and water-rich asteroids bombarding Earth after it formed. Recent evidence suggests water may have been present throughout Earth's history. The ancient zircons from the Jack Hills contain oxygen isotope ratios, suggesting liquid water existed as early as 4.4 billion years ago. Volcanic outgassing released water trapped in Earth's interior to form the oceans. The current thinking is that Earth's water probably came from multiple sources. Some was original, some came from volcanic outgassing, and some was delivered by impacts. The oceans have grown and shrunk throughout Earth's history as water is recycled between the surface and interior through subduction and volcanism. Fact 95. Banded iron formations. Some of Earth's most important iron ore deposits are banded iron formations, distinctively layered rocks with alternating bands of iron oxides and silica. These formations, found in rocks 2.5 to 1.8 billion years old, represent a unique period in Earth's history. At that time, the oceans contained dissolved iron. Photosynthetic cyanobacteria were producing oxygen as a waste product, but the oxygen immediately reacted with the dissolved iron, precipitating iron oxides that settled to the seafloor. The regular banding probably reflects seasonal or other cyclical variations in bacterial activity or ocean chemistry. Eventually, enough oxygen accumulated to oxidize all the iron in the oceans, and banded iron formation ceased. The transition marks a fundamental change in Earth's chemistry, from an oxygen-poor to oxygen-rich atmosphere. These ancient rocks not only provide evidence of early life, but also supply most of the iron ore used by modern civilization. Fact 96. Snowball Earth. Several times in Earth's history, ice may have covered the entire planet, even at the equator, in events called snowball Earth episodes. The most severe occurred during the Cryogenian period, between 720 and South Sea 5 million years ago. Evidence includes glacial deposits in rocks that were at tropical latitudes when they formed. But how could Earth recover from such extreme glaciation? Normally, ice reflects sunlight, cooling the planet further in a runaway process. However, volcanic activity would continue, adding carbon dioxide to the atmosphere. With Earth frozen, weathering of rocks would cease, stopping the removal of CO2 from the atmosphere. Eventually, CO2 would build up to levels that created an extreme greenhouse effect, melting the ice rapidly and swinging Earth from icehouse to hothouse conditions. These dramatic climate swings may have influenced the evolution of complex life, with the Cambrian explosion occurring not long after the last snowball Earth event. Fact 97. Plate tectonics on other worlds. Earth is the only planet in our solar system with active plate tectonics, like we observe here. Mars shows evidence of volcanic activity and possibly some crustal motion in its past, but no current plate tectonics. Venus has volcanic activity but appears to resurface catastrophically rather than through gradual plate movements. Some moons, like Jupiter's Europa and Saturn's Enceladus, have icy shells that may undergo something like plate tectonics, though driven by different forces than on Earth. The presence of plate tectonics on Earth is crucial for maintaining habitable conditions, regulating climate through the carbon cycle, generating magnetic fields, and driving the rock cycle that recycles nutrients. Understanding why Earth has plate tectonics while other similar-sized planets don't remains an active area of research, with implications for habitability on exoplanets. Fact 98. Future supercontinents. Based on current plate movements, geologists can project where continents will move in the future. In about 50 million years, Africa will have collided with Europe, closing the Mediterranean Sea and raising new mountains. Australia will have drifted north, colliding with Asia. In 200 to 300 million years, the continents may assemble into a new supercontinent. Several scenarios have been proposed with names like Pangaea, Proxima, Novopangaea, or Amicia. The exact configuration depends on which way current movements continue and where new subduction zones might form. In one scenario, the Atlantic Ocean would close and the Americas would collide with Africa and Europe. In another, the Pacific Ocean would close and the Americas would collide with Asia. Regardless of the specific outcome, the formation of a new supercontinent seems likely, continuing the cycle that has repeated throughout Earth's history. Fact 99. Geologic time and human perspective. Perhaps the most profound insight from geology is the vastness of geological time. Earth's 4.54 billion years is almost incomprehensible to human minds. One common analogy compares Earth's history to a 24-hour day. On this scale, Earth formed at midnight. Life appeared around 4 a.m. Photosynthesis started around 7 a.m. The first animals appeared around 8:30 p.m. Dinosaurs lived from about 10:55 p.m. to 11:39 p.m. Modern humans appeared at 11:58 p.m. and 58 seconds. All of recorded human history occupies the last few seconds before midnight. This perspective shows how recent humans are in Earth's story and how most of Earth's history occurred without us. It also suggests humility. The processes that shaped our planet operated for billions of years before humans existed and will continue long after we're gone, unless we learn to work with rather than against these fundamental forces. Fact 100. Geology and the future. Geology isn't just about the past. It's crucial for understanding our future. Geologists help locate resources, predict hazards, understand climate change, and find suitable places for infrastructure and waste disposal. As human population grows and resource demands increase, geological knowledge becomes more important. We need to find sustainable ways to extract resources, understand how our activities affect geological processes, and prepare for natural hazards that are inevitable on a geologically active planet. Climate change is fundamentally connected to geology through the carbon cycle, and understanding Earth's climate history helps us predict future changes. The geological perspective, seeing Earth as an integrated system operating over vast timescales, provides context for human activities. We are not separate from Earth's geology. We are part of it, capable of influencing geological processes at scales that would have been unimaginable a century ago. This power comes with responsibility to understand and respect the planet that is our only home. And there you have it. 100 facts about geology, 100 windows into the story of our planet. We've journeyed from Earth's molten core to its frozen poles, from the birth of the planet 4 billion years ago to predictions of future supercontinents hundreds of millions of years hence. We've explored mountains that rise and fall, oceans that open and close, continents that drift and collide, and life that appears, evolves, and sometimes vanishes in catastrophic extinctions. The earth beneath your feet is not the unchanging foundation it seems. It flows, shifts, breaks, and remakes itself constantly. Mountains are young, ocean floors are even younger, The continents have danced across the globe, joining and separating in an eternal cycle. Rocks form, erode, and form again. The atoms in your body were once part of ancient rocks, ancient life, perhaps even ancient stars. Geology teaches us patience, showing us processes that operate over timescales that dwarf human experience. It teaches us humility, revealing that humans are newcomers on a planet with a vast history that unfolded without us. It teaches us wonder, showing that even the most familiar stone has a story stretching back millions or billions of years. It teaches us connection, demonstrating that everything on Earth, from the deepest ocean trench to the highest mountain peak, from the oldest fossil to the newest volcanic island, is part of an integrated system. As you drift towards sleep tonight, remember that you're resting on a thin crust floating atop a mobile mantle, driven by heat from a core as hot as the sun's surface. Remember that the ground beneath you is moving imperceptibly, slowly but inexorably, carrying you on a journey across the planet's surface. Remember that every rock, every crystal, every grain of sand holds a story if you know how to read it. The Earth is not just where we live. It is a dynamic, ever-changing world, and understanding its geology helps us understand our place in the vast expanse of time and space. We are temporary inhabitants of an ancient planet. But while we're here, we have the privilege and responsibility of understanding, appreciating, and protecting this remarkable world. Sleep well and dream of deep time, of stone that flows like water, of mountains rising from the sea, of ice sheets advancing and retreating, of life evolving and adapting through countless generations. The Earth has been here far longer than we have, and it will remain long after we're gone, continuing its slow, majestic dance through time. Thank you for spending this time with us here at DreamLab Knowledge. If you enjoyed exploring these 100 facts about our planet's amazing geology, please like this video and subscribe to our channel for more fascinating explorations of the natural world. Your support means everything to us and helps us continue creating content that brings wonder and knowledge to your evenings. Until next time, rest well and carry with you a deeper appreciation for the ancient, dynamic planet beneath your feet. This is DreamLab Knowledge, wishing you peaceful dreams and a curious mind. Good night.